Two more types of reactions, acid-base and gas evolution. These types of reaction can also happen from the switching of partners. You may have heard of those types of reactions as double displacement, where the two couples come to a party and both couples get mixed up, displaced. And so we can predict the products forming in the same way. The acid-base reaction is also called a neutralization reaction. You get an acid reacting with a base, and as a result, they neutralize each other. What you get from that is usually water and a salt, an ionic compound. Gas evolution reactions produce a gas. They evolve a gas, often seen as bubbling or fizzing or sometimes as a smell or a color. There are different definitions of acids. We're going to use the Arrhenius definition. You do not need to remember that name. Arrhenius was a scientist who came up with this definition. So the Arrhenius definition is that an acid is a substance that produces H plus in aqueous solution. So an example would be hydrochloric acid, HCl. What happens is it ionizes. It is not an ionic compound, but it forms ions, it ionizes. So we tend to think of it this way as the hydrogen ion coming apart from the chloride ion and they're separating. Well, let's think about what is a hydrogen ion. How many protons does hydrogen have? One proton. How many electrons does a hydrogen atom have? One. So here I've got the smallest atom, one proton, one electron. There are a couple of isotopes that have neutrons, but the most predominant one doesn't even have a neutron. If it loses its electron, what's left? The proton. The proton is far too small to just be floating around by itself. So what happens is it tends to attach itself to a water molecule. I think of this hydrogen ion as being a little bit like a baby, a very young baby, maybe a newborn baby. You don't see newborn babies just out strolling the streets by themselves. Right? They're always with someone. And the hydrogen ion can't be alone in solution. It's going to be carried by water. And when that happens, you have H3O, and now it has a positive charge, and that's called the hydronium ion. And here's an illustration of the hydronium ion. So here's a water molecule, and you can imagine this hydrogen ion just hopping on, getting carried around. Most chemists use H plus and H3O plus interchangeably because there's water present and we just understand that H plus is too small to be out by himself. Writing H plus instead of H3O plus makes a lot of the equations simpler, and so it's just something we keep in the back of our heads. And I'm sorry if it ends up being confusing for you, which it probably will, but we'll get through it. Polyprotic. So a hydrogen ion is just a proton. Polyprotic means many protons. These are acids that have more than one ionizable hydrogen. So an example is H2SO4. There are two ionizable hydrogens. So one molecule of sulfuric acid can give off two hydrogen ions. It's called a diprotic acid because it has two hydrogens. And kind of as a disclaimer, the first ionization is considered a strong acid. The second one is a weak ionization, but I don't think we're going to have to worry about that much. What's an Arrhenius base? It's a substance that produces hydroxide ions in aqueous solutions. So the ones we're most familiar with are things like sodium hydroxide. It's a soluble metal hydroxide. It dissociates, it dissolves, forms hydroxide ions. But there are other bases, like ammonia, that are bases. They do produce hydroxide ions in solution, and yet they don't even have hydroxide in them. How does that work? Well, again, writing with the eraser, not so effective. NH3, we put that in water. What the NH3 is going to do is it's going to steal a proton from water. It's going to steal a hydrogen ion. So it's going to become ammonium ion, and then what's left of the water is hydroxide ion. So the ammonia produces hydroxide by stealing hydrogen ions from the water. And there are some bases that produce 2 moles of hydroxide per mole of base. They don't actually have a special name like diprotic or anything. So let's look at these reacting. What happens is the hydrogen ion produced by the acid combines with the hydroxide ion produced by the base to make water. So here we have HCl plus sodium hydroxide. So in aqueous solution, we get this forms H plus and Cl minus, and the sodium hydroxide forms Na plus and OH minus. We can predict the products by swapping partners like we did with the precipitation reactions. We could have the sodium ion with the chloride ion and the hydrogen ion with the hydroxide ion. And then, if you're a little foggy because you didn't get enough sleep last night, and you look at H plus and OH minus, and you say, oh, well, opposite charges equal in magnitude, push them together. And you look at HO, and you say, huh, that's funny. Oh, wait a minute, that's water, H2O. But it's the same idea as with the precipitation. You look at the ions that are formed and you swap the partners. So whenever you have to predict products of a reaction, that should be the first thing you try. It doesn't always work, but it works a lot. If you look at the ions here, so this becomes water. If we're writing a net ionic equation, that does not separate into ions, so we're not going to do that. This is a soluble ionic compound, soluble, soluble, and then if we cross out spectators, sodium is a spectator, chloride's a spectator, and this is what we're left with down here. So most acid-base reactions will end up with a net ionic equation like that. The exception would be if you have a weak acid or possibly an insoluble salt that's formed. Any questions?
You said look at the partners and
Switch partners.
Okay.
So we have a guy and a girl, a guy and a girl. We're going to mix it up and form 2 new couples. Here's an illustration of what happens when we're doing that. Here we've got hydrochloric acid. What it actually looks like in solution is we have chloride ions, and the hydrogen ion that comes from that is not out by itself, it's riding on a water molecule. Okay, it's being carried around. And here we have sodium ions and hydroxide ions floating around. When we mix those 2 together, the hydronium ion and the hydroxide ion get together. And the hydronium ion is saying, hey, I've got this little kid with me. And the hydroxide ion is saying, hey, I don't have my little kid. Hey, we'll get together. I'll take your little proton, and then we'll both be great again. It'll just be H2O. And so that's what they do. So it neutralizes. And then we're left with chloride ions and sodium ions just floating around like they were before. Any questions? Okay, so here's that table that I need to remember to move up in the slideshow. Strong acids. And these are strong bases. So okay, gas evolution reactions. These come in 2 forms. One form, you get a gas forming directly by ion exchange. So this is an example, K2S reacting with sulfuric acid. You swap the partners, you get K2SO4, and you get H2S. Now, I would expect you to look at H2S and think, oh, that's an acid. Well, technically, it is an acid, but it's just going to bubble out of the solution and act like it's going to be a gas. So how do you remember that? You make a flashcard and you memorize it. It's a very smelly gas. Anything with sulfur in it tends to stink. The other types, you do the swapping partners, and then you get something like this, H2CO3. That's an acid. It's carbonic acid. Carbonic acid is not stable. It decomposes spontaneously. It falls apart into water and carbon dioxide. We should remember that carbon dioxide is a gas. How do you remember that H2CO3 is unstable and decomposes?
Flashcards.
Flashcards. Yeah, you just have to remember it. Sorry. So this is what would happen. Sodium hydrogen carbonate, this is baking soda in water mixed with HCl. And when those mix together, the hydrogen ions in the hydrogen carbonate ions form carbonic acid, which immediately begins to fall apart into water and carbon dioxide, and we see the fizzing of the carbon dioxide bubbling out. So there are three intermediates that you need to recognize. Again, flashcards. There's our carbonic acid, H2CO3. This is sulfurous acid, H2SO3. Also not stable, and ammonium hydroxide. So if you do that double displacement switching partners thing and you end up with one of these, you have to decompose it and write its products, which is actually not as hard as it seems because they do follow a nice little pattern. So I'll show you what this pattern is. So the first one, H2CO3, when that decomposes, it falls apart into a water molecule and what's left. So if I take this and I take out the H2 and I take out one of the O's, what do I have? CO2. And that's my gas. Same thing happens with H2SO3. It decomposes into water and SO2. And that's the gas. And ammonium hydroxide doesn't look the same as those two, but it does a very similar thing. It decomposes into water and what's left. So if I cross out this oxygen, this hydrogen, and one of those hydrogens, I've got ammonia left. Another smelly gas. Yeah, water comes off and whatever's left. So you memorize these guys and that H2S just is a gas. And then to do the decomposition, you take off the water and you write down what's left. Now, this is certainly part of the class, and if you want an A in the class, you're going to have to remember this. If you're having trouble, if you're struggling and you're just trying to get through, this is one of those things that you could skip over and it wouldn't be the end of the world, okay? But that whole switching partners, predicting products, writing net ionic equations, focus on that. That's more important. This is important, but it could be optional. Let's do an example. Write a molecular equation for the gas evolution reaction that occurs when you mix aqueous hydrobromic acid and aqueous potassium sulfite. Again, with the names instead of the formulas. By the way, I put some, what are they called? I don't know. It's a funky kind of assignment on Mastering Chemistry. It's not the regular kind. It's interactive. I put up, there's actually 5 of them about nomenclature. Those are worth a little bit of extra credit. And even if you just are nailing nomenclature, I would still encourage you to go through and do those. If you're really good at it, you'll get through really quickly. If you're struggling with it, it's going to lead you down longer paths and give you more practice and help you understand. So you really should do those. So aqueous hydrobromic acid. The prefix hydro tells me that this is a binary acid. There's no polyatomic ion with oxygen. So it's bromic from bromine. So I've got the Br and the H+, and so it's HBr. That's the hydrobromic acid. And aqueous potassium sulfite. Well, potassium's K+. Sulfate is SO4, 2-. This is the light version, sulfite. SO3, 2-. So when I put those two together, I get K2SO3. That's aqueous, because it said so right there. They're not telling me what the products are, although they're giving me this big old hint, gas evolution reaction. How do we predict the products? Swap partners. So we're going to put potassium with bromine and hydrogen with sulfite. So here I've got potassium with bromine. So it's going to be KBr. Soluble or insoluble? Soluble. All potassium compounds are soluble. So that's aqueous. And then I've got H+ with SO3, 2-. When I put those two together, I get H2SO3. And your brain should go, ding! That's one of those three things that's unstable.
Becomes a gas.
It makes a gas. So I need to take a water off and write down what's left. So that's going to be H2O, liquid, plus what's left is SO2. And that's going to be the gas. Gas evolution reactions often have this happening where we have a polyatomic ion and it did come apart. Is it balanced? Nope. What's the one that kind of jumps out at you that's not balanced? Potassium. Here I've got K2, here I just have 1. So I need to put a 2 here, 2 KBr. That balances the potassiums. Then I kind of feel like, well, I just did something to the bromine, so I'm going to look at bromines. I've got 2 bromines on this side. How many on that side? Only 1. Well, we can fix that by putting a 2 in front of it. And now we've got, let's look at sulfur. We're going to have to look at sulfur and oxygen separately. So here's 1 sulfur and 1 sulfur, so that's okay. And then the oxygens, I've got 2 oxygens plus 1, that's 3. 3 oxygens here, and we still have to check the hydrogens. 2 hydrogens and 2 hydrogens. We're good. Any questions? Gas evolution reaction.